multiplication. Here, multiply and accumulate unit. Here, the most of the DSP applications require the computation of the sum of the products of a series of successive multiplication. In order to implement such functions mean sum of the products of a series of successive multiplication. Okay, a special unit called a multiply and accumulate unit is required. Okay, a MAC consists of a multiplier and a register called accumulator, which multiplies two n-bit numbers x and y and gives a product 2n bits wide. Gives a 2n bits wide. This is added to or subtract from the contents of the accumulator in the add bar subtract unit. The result is saved in the accumulator. Bunny. Here, after the multiplications, okay, that product is added with the contents of the previous value stored in the accumulator. Here, the max are used to implement the functions of the type a plus bc. Functions of the type a plus bc. If the accumulator is cleared at the start of a series of multiplications, it will contain the accumulated sum of the products on the completion of all the multiplications. At the start of the applications function, okay, the accumulator will be clear. Okay, then at the last it will contain the accumulated sum of the products on the completion of all the multiplications. Okay, this is the block diagram of the MAC unit, which consists of multiplier unit, and also here we have the product register, which can store the partial product value that can be goes to its input to the add or subtract unit. Okay, here the add bar subtract unit, which can add the value from product register and also from the previous value stored in the accumulator. See here, there is feedback from accumulator here. Then again, after addition or subtraction operation, okay, the result can be stored in the accumulator. Okay, although the multiplication and accumulation are two distinct operations, each normally requiring a separate instruction execution cycle, the two can work in parallel. The two can work in parallel. That means here the multiplication and accumulation both are parallel operations. Okay, see here, although the multiplication and accumulation are two distinct operations, each normally requiring a separate instruction execution cycle, okay, the two can work in parallel. At a time when the multiplier is computing a product, the accumulator accumulates the product of the previous multiplication. Thus, if n products are to be accumulated, n minus 1 multipliers can overlap with accumulation. Okay, during the very first multiplication, accumulator will be idle. Okay, and during the last accumulation, the multiplier will be idle. Okay, since all the n products have been computed, thus it takes a total of n plus 1 instruction execution cycles to compute the sum of products of n multiplications. Yeah, how much time it is required? N plus 1 instruction execution cycles to compute the sum of products of n multiplications. Okay, so here if n is large, this work out to a speed of nearly 1 multiply and accumulate operation per instruction cycle execution cycle. ಗೊತ್ತಿಲ್ಲ. This pipeline operation of a multiplier and an accumulator working in parallel to effectively execute a MAC operation per cycle is a standard feature of many commercial DSP devices. Okay, please go through this. It's very important. So many times they ask this question: multiply and accumulate in it. Okay, just note down what it consists of. Then how it will work. How many times of the what are the number of multiplications and accumulations? Okay, here the accumulations and multiplication will take parallelly. Will operate parallelly. Okay, just go through this. Then here overflow and underflow. See here, we know that the size of the accumulator is 2n bits. If it exceeds or less than 2n, what will happen? If it is exceeds, overflow occurs. Okay. If the value is less than 2n, underflow will occur. See here, while designing a MAC unit, attention has to be paid to the word sizes encountered at the input of the multiplier and the sizes of the add subtract unit and the accumulator, as there is the possibility of overflow and underflows. The overflows and underflow can be avoided by using any of the following methods. One is using barrel shifters at the input and output of the MAC unit. Input and output of the MAC unit. And B, providing guard bits in the accumulator. Providing guard bits in the accumulator. Guard bits means we can add some extra bits to the accumulator. Okay. Using barrel shifter, how we can avoid the overflow and underflow? We can do the scaling, scale down or scale up. To avoid the overflow, using barrel shifter, we can do the scale down. To avoid the underflow, okay, we can do the operation of scale up. That means increase the number of bits. Here, the providing guard bits in the accumulator. What is meant by the guard bits? Guard bits means we can add some extra bits to the accumulator. And third one is using saturation logic. We can avoid the overflow and underflow. In saturation logic, what is the most positive number and least negative number which can hold by the MAC unit. Okay, but here we will discuss about the shifters. Shifters are normally provided at the inputs and the output of the MAC unit. The input shifters help to normalize data samples or filter coefficients as they are fed into the multiplier to avoid overflow of the accumulated result at the output. Here, what we can do at the input side of the MAC unit, okay, we can do the normalize. Means we can change some. That means we can normalize means we can scale down. For example, if we divide the input value 1 divided by 2, if we divide the input value at the input side 1 divided by 2, at the output side we can multiply by 2. That is normalize means 1 divided by 2. Okay, denormalize means multiply with 2. See here, likewise, the shifters at the output is used to denormalize the result after the sum of products computation before being saved in the memory. Before being saved in the memory, we can do the denormalization of the output value. Next one is guard bits. Sometimes, in order to preserve accuracy, the inputs to the multiplier are not normalized. In such a case, when repetitive MAC operations performed, the accumulated sum grows with each MAC operation. Okay, This increases the number of bits required to represent the result without loss of accuracy. Okay, one way to handle this growth is to provide extra bits in the accumulator. Provide extra bits in the accumulator. Okay, these extra bits called guard bits. These extra bits are called as guard bits, or we also call it as extension bits. Okay, these allow for the growth of the accumulated sum as more and more product terms are added up. Okay, when the computation of the required sum of products is completed, the extension bits may be saved as a separate word if required. Alternatively, the sum along with the guard bits may be shifted by the required amount and saved as a single word. When guard bits are provided in the accumulator, the size of the add subtract unit also increases correspondingly. Next one is saturation logic. Okay, with or without guard bits, an overflow condition occurs when the accumulated result becomes larger than the largest number it can hold. Okay, with or without guard bits, an overflow condition occurs when the accumulated result becomes larger than the largest number it can hold. Likewise, when handling a negative number, an underflow will occur if the contents of the accumulator become smaller than the smallest number it can hold. In such situations, it may be better to limit the accumulator contents to the most positive value to avoid an error known as wrap around error. Here we can fix the most positive number which can hold, most negative number which can hold. Okay, the overflow underfill occur if the result goes beyond the most positive number or below the least negative number the accumulator can handle. Okay, when the overflow and underflow will occur if the result goes beyond the most positive number or below the least negative number the accumulator can handle. Thus, the overflow underflow error can be resolved by loading accumulator with the most positive number which it can handle at the time of overflow and the least negative number that it can be handled at the time of underflow. Here we can load the most positive number, the accumulator which can hold, and the least negative number, the accumulator which can handle. Okay, a schematic diagram of saturation logic is shown in figure. This is the block diagram of saturation logic. Okay, here in saturation logic, as soon as overflow or underflow condition is satisfied, the accumulator will be loaded with the most positive or least negative number, overriding the result computed by the MAC unit. So here, this is the here Ci is carry into the MSB, C0 is the XOR gate, C0 carry out from the MSB. The overflow underflow condition is detected by monitoring the carry into the MSB and the carry out of the MSB. If carry in is not equal to the carry out, the overflow underflow condition occurs. Just remember here, this carry in is not equal to C0. Okay, the overflow or underflow condition will occur. The selection of positive and negative number is based on the sign bit of the number. Okay, next building block is arithmetic and logic unit. In addition to the shift, multiply, and MAC operations, a DSP is required to carry out several arithmetic and logical operations, along with the shift operations by the shifter, multiplication by multiplier, and MAC operation by MAC unit. Along with, okay, the DSP also carried out several arithmetic and logical operations. These are the operations such as add, subtract, increment, decrement, negate, and logical operations, and, or, not, XOR, compare, that are also implemented in a conventional microprocessor. This means that the ALU of a DSP is similar to the ALU of a microprocessor, but with additional features such as shift and multiply. Okay, compare the ALU of the microprocessor and DSP. Okay, conventional microprocessor and DSP, the only difference is the ALU of the DSP is same as microprocessor, and along with which has some additional features, shift and multiply. Okay, it consists of a status, flag register, register file, and multiplexer. This is the block diagram of the ALU. Okay, status flags. It is important to know the status of the accumulator after arithmetic or a logic operation. This information is used for program sequencing and scaling. The ALU includes circuitry to generate status flags after ALU operations. These flags include sign bit, 0, carry, and overflow. Okay, and overflow management already we discussed in the MAC unit. Features similar to those discussed in the MAC are also required in the ALU for overflow management. These features are generally combined with the status flag. For example, depending on the status of the overflow and sign flags, the saturation logic can come into effect to limit the accumulator contents to its most positive or the most negative. Okay, the sign bit and overflow bit. If it is high, then they exit a overflow. Okay, here then based on this bits, sign bit and overflow bit, the saturation logic which can limit the accumulator size to most positive number and least negative number. Okay, and the register file, a features that improves the efficiency of an ALU is the implementation of a large general purpose register file. Instead of moving data in and out of the ALU to memory during the course of an arithmetic computation, it may be faster to have intermediate results of arithmetic computation stored in the ALU until the computation is complete and the result is ready to be saved. See here, what will happen using the register file? Sometimes while during the processing, okay, the data will be moved out of the ALU and stored in the register. Instead of that, register means memory. Instead of that intermediate result can be stored in the register file. That register file which can hold the some intermediate results values. When it requires, which can access from the register file. This is about the ALU. Okay, thank you.